toxicity test. And then we're going to third look at procedures for evaluating evidence for climate change attribution. This is something that a few of you have already read ahead and done, but it's going to be sort of the third section of the sequence. So consider this an exciting preview of what we'll be doing over the next day or two. So as we left off last time, we were looking at the global carbon cycle in terms of sort of these key pools or key reservoirs. There's a terrestrial one, vegetation, soil. There is a bedrock one consisting largely of fossil fuels, and then sort of an atmosphere-ocean component as well. So sort of these three major areas. This is not a terribly exciting carbon cycle diagram. This one's much more exciting because this one actually has a diagram or a cartoon of the Earth, which sort of does a nice representation of the fluxes. You can see an atmospheric component going into plant biomass, taking its way down to still carbon. You've got microbial respiration, composition, the flux of the atmosphere. You've got this air-sea exchange, which is moves a lot of carbon on an annual basis back and forth. That's more or less the net wash. And then sort of these fluxes within the ocean, down the ocean sediments, and so forth. So the carbon cycle is sort of important in and of itself, and even if it was 100 years ago and we weren't getting into climate change biology at all, we still talk about the carbon cycle as one of these global nutrient cycles or biogeochemical cycles. But it's taken on increasing importance. This particular global carbon cycle has taken on increasingly importance because of its association with climate change. And specifically the amount of carbon that's ending up in the atmosphere, primarily as carbon dioxide, but also secondarily as methane, CH4, is accounted for a gradual rise in global temperatures. And the way it works is terribly complicated. Actually, it is very complicated, but in broad strokes, it's fairly simple. The general idea is CH4, that is methane, carbon dioxide, and a few other trace gases we'll get into a bit, act as greenhouse gases. So as visible light basically passes through the atmosphere, that visible light transfers energy to the surface of the Earth, warms things up, and in some cases, some of that light is reflected back as visible light. A little bit more about that later. But a lot of it ends up getting absorbed and re-radiated back out as infrared or longer-wave radiation. And while you have visible light that's able to pass through those greenhouse gases end up getting agitated or start vibrating when they start receiving that long-wave infrared, and they end up reflecting some of that infrared heat back down to the Earth. So you end up with light coming in, some of it going out, and some of it sort of bouncing back and forth. So as we continue to add additional greenhouse gases into the atmosphere, that's creating more opportunities for heat to get trapped. A little bit of greenhouse gases is very good. Keeps our planet a lot more than it would be otherwise. But as it continues to rise, it's posing some challenges for the future. So the greenhouse effect, combined with rising carbon dioxide levels or increasing amounts of carbon in the atmosphere, is the fundamental driving factor behind climate change. So it's just this one relatively simple flux of CO2 and methane sort of back to the atmosphere, which makes up a relatively small component of the overall carbon cycle, but one that ends up having some pretty broad effects in the grand scheme of things. So let's start off with a question. So you know from Intro-bio and from long before that, from sectional physiology, ecology, that carbon dioxide is a precursor to photosynthesis. But at the same time, we know carbon dioxide ends up accumulating in this atmospheric pool. So each year, the amount of carbon dioxide in the atmosphere is growing a little bit. And every year to teach this darn course, I have to come back and revise this slide and stick a new number up there at the blue dot. So this terminated in the year 2014, 398 parts per million. Last year we were at 407. This year, as of 2 days ago, we're at 408 parts per million. Next time I teach, it'll probably be about 410. So why aren't plants responding to this increase in carbon dioxide and taking that up? Why is that?
Does that also increase the heat? Then as we learned, one of the ways to reduce heat, with their increase in heat, you also get an increased water loss, and so they need water to stay alive. They have to like manage the photosynthesis.
Your reasoning is absolutely correct. Okay, so with the rising heat, that can end up inhibiting photosynthesis. However, if you look sort of across the whole globe, the amount of heat, even during the growing season, is not all that great where most plants live. Basically, it's not reaching levels that are resulting in that sort of thermal shutoff. So your reasoning's spot on, but not applicable in the broad sense.
So is carbon ever a limiting factor for plants in the first place? If it wasn't, they wouldn't be responding to it if it was already enough that they didn't need more of it.
So what else could be a limiting factor for plant growth?
Nitrogen in the soil.
Okay, nitrogen in the soil.
Phosphorus.
Phosphorus.
Phosphate to an extent. Iron. Magnesium.
Iron in the oceans for phytoplankton mostly.
Hydroponic plankton.
Yeah.
Antiponic.
So, if we have a situation where carbon dioxide is not limiting, if there's some other limiting nutrient coming into play, then in those cases, adding additional carbon dioxide is not going to result in an increase in growth. And again, your reasoning is spot on. And I want to sort of throw out sort of a counter argument. You make a very good argument. Here's a counter argument. Basically, in the 1990s and 2000s, there was a big trend in ecological research called they were called face experiments. They did not involve people spaces, or even animal spaces. But I'm trying to remember exactly. Free air carbon enrichment. So that's what FACE stood for. Free air carbon enrichment. So what people did was they basically set up these big rings that might be about as big as this classroom, and in there they basically sort of pumped in this carbon dioxide into these plots. Then they sort of sat back and sort of watched what happened to the plants and what they were trying to simulate, and they got good at it more or less in terms of control. They were trying to simulate an enriched carbon dioxide environment for these plants. And face experiments took place in grasslands, it took place in forests. It got to the point where, I was often cursing, saying like, not another face experiment getting funded. I mean, come on, how much can we learn from these things? My research on wolves, which is far cooler, was not being funded. Face experiments, right? So anyway, when they did these face experiments, they observed in a lot of cases that the plants initially did grow more compared to areas without the carbon dioxide enrichment. So the initial response to these was like, plants appear to be taking up this increase in carbon dioxide. What ended up happening was you ended up seeing a little bit of a boost in growth, not a great boost. But what do you suppose might have happened as those plants started growing faster?
Other nutrients, we need more other nutrients such as
nitrogen to help grow and phosphorus.
Okay, so that's one thing that happened. They basically started peaking out as they started growing faster. The demands for other nutrients sort of increased. So they got this initial boost and they sort of plateaued. One of the other things that happened, which I wouldn't expect you to know, was they ended up producing a lot more volatile organic hydrocarbons. I'm sorry, not hydrocarbons, molecules, mainly ozone, which ended up sort of feeding back into the system and inhibiting plant growth. Because ozone, ground level ozone, is highly oxidative and ends up sort of slowing down photosynthesis. So you can sort of start off, doing some armchair ecology and think to yourself, well, put more carbon dioxide into the atmosphere, and we know plants need carbon dioxide, and therefore everything's going to grow more. But when you actually do the experiments and get into it, you start seeing that, well, there's sort of limitations to that. You can run out of nitrogen, and that'll limit your growth. You can end up in places like some of the shortgrass prairies, they ended up experiencing water stress. It wasn't nitrogen, but there wasn't enough water to support that extra growth. And I always wanted to put in the proposal just to be a wise guy. I always wanted to set up a phase experiment in the Sahara Desert, right, where there's no vegetation at all. Right? The idea is like, oh, more carbon dioxide, you'll get more plants. Why wouldn't a phase experiment work in the Sahara Desert? There's no water, and almost no vegetation. So, yeah.
So if you try this with cameras for plants in a more water-rich environment, you will see better growth if you monitor the other nutrients.
If you were increasing nutrient content of the soils and there was adequate moisture, certainly carbon dioxide would act to increase growth. And in fact, I can say this out loud now, as recreational cannabis is legal in a number of states, and medicinal cannabis is legal in even more states. People who grow cannabis commercially will often be inside of warehouses or greenhouses. They'll be adding nutrients, they'll be adding moisture, and they'll also be adding carbon dioxide to accelerate growth of those plants to increase overall yield. And it ends up being economically viable to provide those plants with extra carbon dioxide in a nutrient-rich environment to boost overall growth. So under optimal conditions, it doesn't have to be a C4 plant, but if you have a gardener sort of taking care of you, carbon dioxide can boost growth of plants overall. However, in the real world where there's herbivores and there's pathogens, and there's moisture stress and there's nutrient limitation, you don't get this nice translation of increased carbon dioxide resulting in increased plant growth. It just doesn't happen. It happens a little bit, but it sort of plateaus out pretty quickly. And so as a result, the number of plants that we have out there in the world is not adequate to offset the amount of carbon dioxide that's being emitted through industrial processes, through our cars, through other fossil fuel combustion. And as a result, we're seeing each year that carbon dioxide is sort of itching out a few more parts per million per year, probably a little more. Any questions on plants and CO2? I want to take sort of just a brief detour, provide some enrichment here for some stuff that's not in the text. The idea of climate change is not a new idea. And in fact, sort of the first reference of climate change dates back to 1896 in this paper titled, very exciting title, On the Influence of Carbonic Acid in the Air Upon the Temperature of the Ground, by Professor Svante Arrhenius. A very strange title, but carbonic acid in the air is referring to carbon dioxide. It's 1896, different words. Yeah? Yes, yes. You may know Arrhenius from such famous courses as chemistry. It's the same guy, acid-base chemistry Arrhenius, same Arrhenius. That's probably why it was all in carbonic acid. So anyway, there's this sort of interesting quote here, which I have highlighted from the paper, and this is written 1896 style. But it says, one may now ask how much of the carbonic acid, or carbon dioxide, vary according to our figures in order that the temperature should attain the same values in the tertiary and ice ages respectively. Okay, we know what the ice ages are. It's a period from about 2.7 million years ago up to about 10,000 years ago. But what's the tertiary? No Earth environmental sciences students in here.
On the asteroid bubble dinosaurs.
Well, if one was to start the calendar of the tertiary, that's when it would technically start. It would start 65 million years ago, and it would run up until the last ice age. So, and tertiary is sort of an outdated term now. The geological calendar has been updated. The Paleogene, Eogene, but that's just Arrhenius didn't foresee that coming. This is over 100 years ago. Anyway. So when he's talking about the same values as the tertiary and the ice ages, he's talking about temperatures basically over the last 65 million years, which surprisingly, in 1896, we had a reasonably good handle on. We could get information about past temperatures, maybe not in terms of magnitude, but we knew the tertiary was warmer based on the fossil record and the idea that we were finding tropical fossils way up in temperate latitudes. Now we knew during the ice ages, around this time, we knew that the ice age was sort of a more recent phenomenon, due to records of pollen and some other fossil records as well. So not a lot of the details worked out, but aware of this geological period and the idea that temperatures have changed in the past. Anyway, so back to Arrhenius, he says a simple calculation shows the temperatures in the Arctic regions would rise about 8 to 9 degrees Celsius if the carbonic acid increased 2.5 to 3 times its present value. So he's writing right around here. So our estimate of CO2 in the atmosphere is around 290 parts per million. Right, so a rise of 2.5 to 3 times that value is more or less what we're on track to see by the end of this century, under a scenario of just keep ignoring climate change and not try to do anything about it. Maybe the next generation will deal with it. If that's the overall strategy that nation state and state state and whatnot, that puts us on a track for that 2.5 to 3-fold increase in carbon dioxide over those 1896 values. So he also writes, in order to get the temperature of the ice age between the 40th and 50th parallels, the carbonic acid in the atmosphere should sink to 0.62 to 0.55 of its present value, lowering the temperature 45 degrees Celsius. So this is sort of the first time that someone's putting together some equations and linking the sort of the heat trapping effect of carbon dioxide in the atmosphere to past climates. The idea with less carbon dioxide, air temperature is going to be colder. With more carbon dioxide, air temperature is